All right, welcome to Computer Science 305. This is Programming Languages, and today we're going to be taking our last look at Prolog. And so we have a few things to talk about, specifically numeric computation, Prolog, problem space search, focusing on difficult problems known to be our decision and optimization problems. And then finally we'll say our farewell to Prolog and hopefully be done with this language, excluding the lab that you have left to do. So in Prolog, we have oftentimes we have unevaluated terms, right? So we know that Prolog operators allow terms to be written more concisely in a infix rather than a postfix, prefix way of writing things, but or a combination thereof. But we know that even then, these things, for example, as we see in each one of these different terms here, they are not actually evaluations. These are terms that will basically form the basic concept of an atom, right? Well, for the most part, except for plus is an operator, so it actually acts as a compound term. But the problem here is that these by themselves will not unify with 7, right? So that's not necessarily a good thing. What we need to do is we need to figure out a way that we can actually execute this value so that we can actually get execute these expressions so that we can actually get the values that we need. And so if we want to do that, we can use the is predicate, and it's used to evaluate a term that's a numeric expression, takes two parameters, right, and evaluates the term y and unifies x with the resulting atom. So it is usually used as an operator. We can sit there and run that really quickly and validate that this actually does work. And we do that by saying, well, we have to run the Prolog. So let me just change directories to Prolog 3. And then, so we say x is 1 plus 2 times 3 times 3. We see that we get x is 7, right, as we expected. So we know it's usually used as an operator, as we see here in this definition, where it's in the infix notation. We need to know that instantiation is required, right? So meaning that we actually have to have these things associated with a value, or unified at least, to the point to where they can do that. And so we can also say, for example, y equals x plus 2, and x is equal to 1. And that gives us the values we see here. Now, if we, on the other hand, if we say y is x plus 2, x equals 1, that will cause an error, right? Because x hasn't been unified with anything yet. So we get the error that we expected, saying that arguments are not sufficiently instantiated. But if we were to reverse the order, saying x equals 1 first, which unifies x with 1, and then we say y is x plus 2, we get the instantiated values, or we get the actual atom values for each one of these, which is great. Now, we have valuable predicates, so we can say for x is y, the predicates that appear in y have to be evaluable predicates, right? This includes things like predefined operators, as well as other predefined evaluative or evaluable predicates like the absolute value and square root predicate. So if we have those, we can then start doing some actual work with numbers, right? So we can say x is 1 over 2, and then x is 1.0 divided by 2.0, or x, sorry, with a period, or x is 2.0 divided by 1.0, which then gives us the 2.0, right? Now, one thing we need to know is that Prolog is dynamically typed, right? So x is taking on the value where it was originally an integer, now it's a real. The interesting thing is that almost all these evaluable predicates are overloaded for all combinations, and that types are resolved at runtime through this overloading. But thing we have to note is that literal values like literal or atoms are not equal, right? So if we have, as it shows here, if we have 2 equals 2.0, and we try to do that, it won't unify, mainly because they're two completely different atoms, right? They're not the same value. We also can do numeric comparison using all the standard operators. Note that the equal colon equal is the equality operator, and the equal slash equal is the not equal operator. When we utilize these, effectively both sides must be instantiated to a numerical atom. So for example, we can do, if we attempt to use this on a simply 1 plus 2 is less than 1 times 2, that will cause us an error, right? Because these are not fully evaluated terms. So we run that and we get false as expected. If we if we actually have an instantiated term like x, right, which is we'll say 1 minus 3 as the example shows, then y will say just is 2 straight up. If we check if x is sorry, we make that negative 2 straight up. If we say x equals y, right, it should give us the should unify them, and it does. States that x is equal to y and y is equal to negative 2, which we expected. If we were to run this again with the slash, we would get false as expected. So there are equalities in Prolog, right? You have so far we've used 3 different but related equality operators. We used x is y, which evaluates y and unifies a result with x. We have 3 is 1 plus 2, which succeeds, but 1.2 is 3 fails, right? Because 1 plus 2 is not instantiated. X equals y unifies x and y with no evaluation. X equals colon equals y evaluates both and compares both, right? And then we have the equal slash equal evaluates both and compares both to check if they're not equal. So we have to make sure that we are aware of that. Any evaluated term, so it must be something that is evaluated, must be fully instantiated. Then we can move to an example, right? So now we want to actually calculate something to give us a value. So we can start with defining my length. So we'll actually do that in a file, and we'll run it as we need to. Let's call this my length. So in here we say my length 0, and then my length right. So what this is saying is basically that we are going to recursively call my length, updating tail len, and then we're going to say len is tail len plus 1. Pretty simple, right? It's just going to walk all the way along the list, updating the length as it goes. And so if we save that and go ahead and run it, and we execute my length on ABC, X as we see in the example here, we get 3, right? Now the interesting problem is if we attempt to run, if we say 3, right, and then X in 3, it will generate a list with 3 random, well, not random, but 3 atoms that it will create for us, which we see here. Actually, I wonder, will it give us multiple? It does not. Anyway, I won't kill that. That's no good. I think I may have broke it. So, moving along. A counterexample would be if we were to simply, we'll reconsult that. We'll go ahead and compare. Oh, yeah, so if we said len equals tail len plus 1, right, instead of len is, there's no evaluation here, and thus len would be showing us the full equation that would be used to calculate. And so if we go ahead and make that minor modification, maybe go ahead and consult. Oh, I actually need to get out of that, and we'll say Prolog 3, and then run Swipple again. And we say my length 1, 2, 3, 4, 5 x. It gives us, as we see on the screen, right? And that should be expected by all means. We can also sum across the list pretty easily. Go ahead and I'll load up a new file. Call it sum.pl. And this one's pretty simple, right? It's just if we have an empty list, we assume the value is 0, and then we sum. We have to look at head this time, and tail. We're going to try to unify with x to give us the value based on the fact that we're looking at sum, tail sum, and x is head plus tail sum, right? Pretty simple, easy to understand. Go ahead and consult that. And we get true. So, looks pretty good. So we say sum, just put in nothing. Just to validate, we get 0 sum, and then 1, 2, 3 should return 6, right? X, we see 6, and then we say sum 1.1, 2.3, and 3.4, right? So that should be what was that? 3.4 plus 3.4 would be 6.8, and we get effectively 6.8, right? Floating point numbers aside, and their problems, we get 6.8. So it looks good. Now, if we want to implement the greatest common divisor function, we can actually pretty simply do that. We'll create GCD. So now, when we put this in, we want, you see the note here says, note, we're not going to use GCD XXX, right? We have to put in X, Y, and Z because we can have all sorts of different numbers that we're attempting to find the, for X and Y, we're trying to find the lowest common divisor for those, but, the greatest common divisor for those that is effectively, even though X and Y may be the same value itself, but we don't want to just make the assumption. So we say GCD X, Y, Z, and then in the it's either that we have X is equivalent to Y, and Z is then Z is X. In the next case, we'll take a look at so we say X is equivalent to Y, Z is X. X, and then if we have GCD of X, Y, and then we have the denom. X is less than Y, new Y is Y minus X, right? And then finally we have, which then returns x new y tail calls the greatest common divisor one more time, right? Trying to drive towards our base case, which is x is equal to y. And then finally we say GCD x, y, denom, and then if x is greater than y, we say new x is x minus y, and we say GCD new x, y, denom. Very good. All right, pretty simple, and we have some sort of small error. This thing. All right, there we go. Consult GCD, and then we'll run it on, let's just try 2 and 6. That'll work. Oh, and Z. And so we get 2, right? Okay, so we ran that. If we run it again, we say GCD 5x. It gives us 5. And then we run GCD 21x, which should give us 3. And then finally GCD 105 and x, which will give us 7. And then finally, I guess we can run 91x7, which we would think, as we've seen before, that it will attempt to unify to find the value. But given the way this operation works, it probably would not be able to do it. And so will cause, mainly because of the need for evaluation, will provide us with an error. So this is one of the times when the typical thought on how these actual operations work inside of Prolog will not work. In other words, the more logical way of thinking about this, the declarative approach, may not work when we are thinking more in the imperative way. Now, in this case, we can get rid of a bunch of extra backtracking if we start putting in cuts, right? So for the first two, we can essentially execute the cuts as the last part of the operation, right? So we'll go ahead and update that to include a cut in the first two. Now, this is saying to us that when we have these cuts in place, this test here is no longer necessary, but we'll leave it in just for, clarity. And so it should operate a little bit more effectively. But I'm not going to go ahead. We'll just leave that for where it is. The next one we have is factorial, right? So if we want to calculate the factorial, it's a pretty simple algorithm where we just walk backwards from our value till we get to 1, right? So we'll do that. We'll say we'll define factorial. And it will create the new file. So we just see what we have. New file, fact.pl. And pretty simply, fact x1, x is equivalent to 1. We'll put the cut in to stop it from trying to do this, because factorial is a expensive process in general. We'll say fact x fact. And then we'll go ahead and say if x is greater than 1, then we say new x is x minus 1. Fact new x nf. Fact is x times nf, right? So we walk down and we simply are multiplying each number successfully, starting from the number we were at, working backwards down towards 1. Okay, so a pretty simple algorithm, right? We all should know this. It's the recursive factorial algorithm. Once we do that, we'll load it up. All right, and then we can just simply run this on 5. Get 120. We run it on 20. We see a huge number. Very quickly, actually. And then if we run it on -2, it will give us an error, right? So we say fact -2 x. It tells us false, right? So which we should expect. So this is the numerics, right? It's pretty simple to use this. We just have to be sure that we're evaluating it using either is or one of the evaluable or evaluative operators, like the equivalence operator, equal, or equal/equal. And so we'll be able to get the values that we need. So it works out. So now, once we have that, we can get ourselves to some more difficult problems, right? And so the first one, and so this is the problem space search, right? And then we all know that obviously Prolog strength is not its numerical computation, but rather its logical or problem space search, right? Given that all it does is it searches through and tries to unify things. So if we can give a logical definition of a solution and then we can let Prolog find it, we're really using the straight up capabilities of Prolog in the best possible way. So in order to do this, right, one of the more difficult problems is what's called the knapsack problem. So basically, we think about this, right? We have a bag or a knapsack that we can fill things with, but we only can fit so many things in there. And our goal is to essentially optimize this such that we select the things that will last. Well, in this case, we're going for a camping trip, right? And we have a pantry filled with items. And so we can only fit in things that are less than or equal to 4 kilograms while trying to maximize the number of calories, right? So we have like some bread, that's 4 kilograms at 9,200 calories, pasta at 2 kilograms, 4,600 calories, peanut butter at 1 kilogram, 6,700 calories, and some baby food at 3 kilograms and 6,900 calories. So if we have this, right, then our goal is to try to figure out how do we walk through all these different possible combinations while and then ensuring that we are collecting the highest caloric level possible. So the greedy method would be going for most calories first, right? So you select only the bread, right? It maximizes the weight out and gives us a really high caloric intake. Or we can choose lightest first. We pick peanut butter, then pasta, which gives us 11,300. But the best choice is actually the peanut butter and baby food, right? So a moderate weight for the baby food and the lightest item, the peanut butter, but with the combined 13,600 calories. So we have to. So there's two ways to look at this. We could try the greedy or the lightest first, or whatever, some heuristic, which are the first two, or the other one is to work all possible combinations until we find the maximum one. But that requires you to search all the way through that space. If you have a large number of possibilities you can take, that becomes an extremely difficult problem to solve. I believe it's actually in the class NP. So no algorithm for this problem is known that always gives the best answer and takes less than exponential time, right? It's in the class NP. So brute force search is nothing to be ashamed of here. That's good since search is something Prolog does really well. Which brute force was exactly what I was just talking about. So what we can do is we have to first define a representation, right? We need to represent each of the items in our database, if you will. And then we create a pantry, which is essentially just a list combining each one of our different items. And it's also, interestingly enough, the same representation we can use for the knapsack, which is a list of items we can take. So let's quickly do that really, and we'll build that up. So we'll create the knapsack problem. Okay, so I'm not going to fill in all the comments. We just have weight. So this is going to give us the value for the weight. Given a list of food items, so either the knapsack or the pantry, and then we can calculate that by saying weight rest W, where X is W plus rest W, right? So it's the rest of W plus the current value of W will be stored in X. So once we have that, then we're done with that. We then also need to be able to calculate the calories, right? So calories, we'll take in a list of items, and we'll then calculate that up just in the basically the exact same way weight's calculated. So calories would be food underscore C rest and then X, right? So we'll store that value in X. So calories rest C, X is C plus rest C. All right, good times. So we're done with that. All right, moving forward. We also need to look at subsequence, right? So we want to be able to find the subsequence of a list, which is basically a copy of the list with the number of elements omitted, right? So the knapsack then must be a subsequence of the pantry, right? So we can define that by saying subseq takes in a list, right? Or sorry, two lists. Okay, so basically we're saying it succeeds when list X is the same as list Y, but with 0 more elements omitted. This can be used with any pattern instantiation. All right, good times. So we've gotten this done. Now we have to, we can validate this. Let's go ahead and check it, right? I'll put our food items in there. We'll do that really quickly. And we say food, bread, 9200, and you know, let's hold on. Maybe we'll just we'll wait that one out for just 1 second. We'll come down here. We'll try out the subsequence. I'm assuming that this might work. Say consult knapsack. All right, very good. We can run the subsequence subsec just to validate. We say 1 3. And then 1 2 3, right? So this should return true because the list 1 3 is a subsequence of the list 1 2 3 4, right? Okay, good. And then if we run it again, right? We're now trying to find what is a subsequence of the list 1 2 3, right? So all possible combinations would be the empty, any one of the individual items, any pair of items, or the entire list itself. And so we run that, and lo and behold, we find all possible subsequences, right? So it can do more than just test whether one list is subsequence of another. It can generate subsequences, which we just did. And this is how we're going to use it for the knapsack problem, right? Because we need to walk through all possible combinations, finding the highest caloric content for the when our weight is 4. So we go ahead and do that, right? We create the knapsack decision now. So that is knapsack decision. So this is going to solve the decision problem, right? The question is, given a pantry, can we, with a capacity and a goal, and then a knapsack, right? Which is what we're going, our end goal, right? We want to say, can we walk through, is there ever a place in the, is there ever a subsequence of the pantry that can give us, that maximizes, that reaches our goal for the given capacity, right? So, and the capacity and goals just, we want to have a total calories greater than or equal to the goal, subject to the constraint that the total weight is capacity. So, if we can set with those constraints, if we can, is there ever a subsequence of pantry that yields that? And that's all this decision problem solves. So you say pantry, capacity, goal, knapsack, right? Okay, so now we've defined what our solution would look like to this problem, and then we can go ahead and we'll run that in just 1 second. So we reload that, and now we can say x equals food pasta to 4,500, food peanut butter 1. Oh, sorry. Hello. What am I doing? We say bread. Let's try this. I need to apparently read knapsack decision, and then we'll go ahead and say food bread for 9,200. Food pasta to 4,500. And food peanut butter 1,6,700, and finally food baby food 3 and 6,900, right? And then we'll say our goal is our weight limit is 4 and our goal is 10,000, and X is our knapsack. And it yields us the answer pasta 2, peanut butter 1, which is the lightest weight, right? And then we could also find peanut butter and baby food, which is, as we identified, probably one of the best goals. And then there's nothing else would yield us with such a high level, right? So this the problem here is this decides whether there is a solution that meets the given calorie goal, but not exactly the answer we want, right? So this leads us to the difference between a decision problem and an optimization problem. The decision problem just tells us whether there are possibilities that will solve that. The optimization problem finds the best one, whatever that best one is. So to do that, we have to actually use another predicate called find all, and then we'll apply that, right? Because find all says find all given x a goal and L, which finds all the ways of proving goal. For each, it applies to x the same substitution that made a provable instance of goal, and then unifies L with a list of all those x's. So if we want to count solutions, right, for example, we can say find all 1 subseq 1, 2, L, right? And we'll find all ones, right? This shows there are 4 ways of proving that subseq with an finding all the different possible routes by which we can operate to create a subsequence of 1, 2, right? So in other words, it's counting the number of possible subsequences that can be generated, right? So we collected a list of ones, one for each proof. Now, we want to collect the instances, right? We then would put subsequence x 1, 2 in there. So essentially what it's doing is it's going to, if we look back up here, it's taking whatever's in the first part and it's going to create a list of those as the goal of L. So for each item that it solves, right? So the first and second parameters to find L are the same. This collects all 4 provable instances of the goal. And so I'm not going to go walk through that. Now if we want to collect particular substitutions, we can do that by running, which is a common use of find all. The first parameter is a variable from the second, right? So this collects all 4 x's that make the goal provable, which I think would be similar to what we're looking for and what we want to do. So now we need to make a legal knapsack, right? So what we want to do is we'll go up here and modify this. Say legal knapsack, pantry, capacity, and knapsack. And then we want to say subseq knapsack pantry, where weight of knapsack W, and then we say W is less than capacity. So this gets us close to that problem. Now we have to find, we want to find every possible combination that meets the capacity constraint, right? That's what we're going to do here. And then the next step I'm thinking would be using these possible solutions. We then want to find the one with the largest caloric content, right? The highest number of calories. So we go ahead and save that. We walk down here and look, lo and behold, we want to find a max calories, right? So we take in a list of food terms, unify the result with an element from the list that maximizes the total calories. Makes sense. We're going to use the helper predicate max C that takes 4 parameters, the remaining list of lists of food terms, the best list of food terms seen so far, is total calories in the final result. So pretty simple. Say max C takes in the empty list so far, we don't care, and so far, right? Next we say max C is then a list first, rest, for the best list of food items seen so far. If we don't really care, we say MC, which is the total calories, and then finally the result. And we say calories first C, and we say MC is less than first C. Then we say max C rest first, first C, and result. Right? So if our calculated calories, if our previous calculated calories is less than or equal to first C, then we're going to disregard, we're going to use first C, and then continue along. And first will be our answer, and then we'll look at rest. So we continue, say max C. We look at now this at first, rest, so far, MC, and result. Calories, first C. Now we're looking to see if MC is greater than first C. It is. Then we say max C, rest, so far, MC, result. So if our current one is greater than what we're looking at, then we just disregard the first item and we continue on. And finally, we define max calories, which is what's going to be the instantiation of the instigator of the recursion. We say first or rest result. Calories first C, max C, rest first C, and result. Okay, so now we can calculate the maximum calories. And finally, we get to the capability to actually perform the knapsack optimization. And so how we do that, right, is we say knapsack optimization, taking the pantry capacity and the knapsack. And then our goal is to then we use the find all, right? And so now we're looking for the max calories, right? We're looking for the knapsack. And we're going to create that from the pantry and the capacity using the legal knapsack definition or predicate. To store that in L. And then we'll use the max calories predicate to reduce that down and select the best item out of there, the optimal knapsack from the list of knapsacks. Okay, so using that, we can then run it. And so we continue along. In order to do this, all we need to do is exactly what we did before with the decision. I'm going to consult. Right? Which we had before, but instead of being a decision, we want to use optimization. Right? And oh, I'm missing, I need to get rid of this middle one. And then we run it, and we get the expected answer, which was peanut butter and baby food. And so we can always try to see if there is another one, and of course there isn't. It's giving us the optimal. That was the whole point. Okay, so now the next problem is called the 8 queens problem. I think I will stop there for now, and then I'll let you guys continue.